This is the basic equation to be used in any calculation in pump and turbine. We learned about this equation in Fluid Mechanics 1 last semester, I think, and I hope you could remember all of this or make your self revision about this. First, we must know about rotational speed because blade will rotate at certain speed, so we need to understand the conversion between linear speed and the rotational speed. The very basic idea is U is equal to R omega, which is U is the linear velocity in meter per second, and R is the radius in meter, and omega is the angular velocity in rad per second. And it is also equal to pi dn over 60, which is pi 22 over 7. D is the diameter in meter, and n is the rotation or revolution per minute, RPM. And we need to divide into 6 with 60 here because we must maintain the unit as meter per second. And if the question gives you rotation per second, the terms here will become pi d and s because the 60 here is used to convert from minutes to second. Means that if the rotational speed is already given in unit second, here we could calculate the value of u by pi d and s. Please be careful because normally in pump or turbine question, it will give you rotational speed in RPM. This is the way we calculate the power of pump. So we know power is the force times velocity, and force here is the multiple of pressure and area. And then we multiple again times velocity here. We could say that pressure can be calculated by using the idea of rho GH, and AV here will become the flow rate. So means we could simplify it in pump and turbines chapter here. We could calculate the power by using this equation, rho G, Q, and H. Work is torque times angular velocity, so it is equal T times omega. And work also can be calculated by using the idea of force times distance. Then, in here, when we calculate the power here, so we have rho, G, Q, and H. So the H here is the head. However, in this chapter, we are very particular about head because we have a few types of head here. So what we need to use is the head of pump. It also called as a manometric head. This is defined by British standard as the sum of the actual lift H and the friction losses in the pipe HF plus the discharge velocity head. So it can be written as HM, the manometric head, is the total head of actual head plus the friction loss in pipe and the discharge velocity head. So it also can be written as P2 over P1 over rho g plus V squared V2 square minus V1 square over 2g. So we could get this from the Bernoulli equation. However, for special pumps, allowance must also be made for the velocity of flow towards the suction intake and any pressure differences at the water surfaces in the supply and receiving tanks. Commonly, the suction and delivery pipes are of equal diameter. So in this case, we could simplify that because the suction and delivery pipe, if the diameter is equal, means the velocity is remain constant. It's remain the same in inlet and the outlet here. So the value here will become 0. So we could say that the manometric head here is only equal to the pressure drop. Pressure drop means P2 minus P1, pressure at outlet, minus pressure at inlet, divided by rho g. So this is a few diagrams to make sure that you understand what is the intake head delivery head, suction head, and the overall the manometric head. So for example, we have a system like here. So this is the tank. It is connected with pump, and then it's flow the water here. So here we have the pump head is equal to 0 because the inlet and the outlet here is remain constant. So at here we could say that because this is the intake water level, so it is 4 meters here, and then the pump is capable to move to flow water until 2 meters from the 2 feet from the level here. So we could say that the pump head is 2 meters. And then if you could see here, so this is the suction water level, the inlet water level here, and then the pump capable to bring water until 8 feet here. So mean that it leave around 4 feet here, so the pump head will equal to 4 feet. So and then this is the idea. So if we have pump here, so the total head is the distance from the suction head here to the delivery head. And when we talk about suction head, this is only the water level here to the center point of the pump, and delivery head is from the center point of the pump to the final water level at the delivery area. So this is the a little bit complicated, but the idea is remain the same. For example, we have a water level here, so we have a pump, and pump is capable to bring water until this level. So we know this is the suction head plus the velocity head, because as we know, the suction head is the start here to the water level, and then it's plus the velocity head as we mentioned previously, and then this is the net suction head, and then this is the discharge head equal to delivery head. So and then we have a friction here, and then we have a delivery velocity head. So these three ideas is written in the previous equation. So another term about suction head and delivery head is like this. So we have the suction head here, we have the delivery head, and this is the total head. So here the total head will be equal to the manometric head. So mean that this pump is capable to lift water from this level to this level. So this is the manometric head. So this is again, it could simplify. You could surf into www.pumpfundamentals.com. So we have suction head here, and this is the delivery head, and this is the total head that occur. So this is suction head, this is the delivery head, this is the suction head, and this is the delivery head. So I think this is a very clear picture for you to understand about suction and delivery head.